Welcome back, and today I'm going to go through a demo that I recently made about a small sheep character that can demonstrate tool use in a Unity environment that's built with ML Agents package. So let's go ahead and take a look at what that looks like. So I have this small character here. This is my sheep agent. I went ahead and made it look a little silly just to be fun. And so this is going to be our agent. And the agent lives in this pin. So it's a very simple environment. It's just a big box. Basically, it has a floor and some walls on the side. And the walls aren't so high that the sheep, can jump out of the pin. But the goal, and you'll see if we switch into the heuristic mode, so I'm going to change my settings from default to heuristic. You can see here that as soon as I start the environment, two things are going to happen. This large purple cube is going to appear here, and this watermelon is going to be somewhere up in the air. So if I switch displays, we can see that our sheep agent is over here. There's this cube or tool that the sheep can use to get to the target watermelon. And the agent, is going to use vision to do that. So in this screen here, what we're looking at is what the agent is going to receive as input as it navigates this environment and tries to get to the watermelon target. So the behaviors that this guy can take is movement in any continuous direction. So I'm going to show you what that looks like. So our agent is going to receive visual input through a camera. So this is what the agent is seeing. And if I move the agent around, you can see what this agent is seeing. So he can't quite see the watermelon from this angle. But if he goes towards this purple cube and he jumps and goes forward, he can catch a glimpse of the watermelon. So that is the controls. You can move left or right. Let me switch displays. He can move left or right, and you can move forward and back in the direction that the agent is looking. So the goal is for this agent to push this cube around or manipulate this cube in such a way that allows it to get to the target watermelon. So it's kind of a simple environment. It took me a little bit longer than I was expecting because you have to get all the dynamics right and figure out how to set up the reward. So let's go ahead and take a quick look at what that script looks like. So again, we just have a classic Unity ML agent setup. We're going to import the agent package from the ML agents. I'm going to get all these different things so I can instantiate the right physics and the correct objects throughout the experiment. And as soon as the episode begins, as soon as the environment starts, we're going to place the agent, this sheep, that's this, into a new random place in the pin, and we're going to give it a random rotation, so it's not always looking in the same direction. Sometimes the agent is looking left, maybe looking right, maybe looking wherever in the Y plane, some random rotation. And in the beginning, it's important just to zero our velocity because when we drop the agent in, as soon as it hits the floor, there's going to be some collision reaction, and we don't want our agent sliding all around. So the next thing we'll end up doing is we'll instantiate the cube tool in some random position in the pin, and also instantiate the target watermelon, also inbounds in the pin, but high enough in the Y dimension that the agent cannot reach it without jumping on the cube. So we also want to say that for some reason, if the tool fell out of bounds, it fell out of the pin, because I was having a little trouble with this, just to end the episode and restart. So if this didn't get set up properly, go ahead and restart. All right, so what observations are we taking? We're going to take our local position, so we as an agent should know kind of where we are, not necessarily in relationship to the world, but just in general. I know how many steps I've taken here and there. This is just to help our agent in the learning process. We also generally know our velocity. So any sound animal that the neuroscience community would typically do this test with, they tend to do it with monkeys and birds, where they're given a tool and they have to use that to reach some treat. Those sort of animals generally know kind of their whereabouts and position and how fast they're moving and stuff like that. So I went ahead and added these observations to the collect observations. What you're not seeing here is the vision collection that's being added to the sensor of observations, and that's because it's added automatically with the ML Agents package. So as soon as you put a camera sensor on your agent, it's going to go ahead. I'll just show you what that looks like. If we go over here to the inspector window and we look at our agent, our game object agent, you can see that I have a camera sensor. And it has the sheep vision, which is this large camera you're seeing all the rays spread out here from. So if you see that big white lines, that's the view of the agent. So back to our script. So now we need to figure out how to create actions once we've received our observations. And so what I ended up doing was allowing for continuous control. And one of those controls is going to end up being the rotation. So you're going to rotate, the agent is going to rotate left or right, and then it's going to move forward or backwards in the position that it had rotated to previously. And the third action we're allowing is whether or not we're going to jump. And in order to make it so that our agent cannot just jump up and get the watermelon, it can't do a double jump, we have to say that there's some constraints on the jumping. So can we jump? That's going to depend on whether or not, so can jump, that's going to depend whether or not we have just jumped. So here we take our rigid body, we add force in the y dimension, we can, according to some jumping force, and we can move up. And once we do that, we can't do that again until we come back down and we collide with the floor. So the floor and the tool have a game tag that says floor just to make it easy. And as soon as our agent collides with that other game object, either the tool or the pin's floor, we set can jump to true, which means that we're able to jump again. This just prevents double jumping, so the agent is forced to use the tool if it wants to get to the watermelon. And another thing that I ended up doing, I think this is a much easier way to do it. I use an on trigger enter for our collider. So our agent here has a rigid body on it, and the watermelon also has a rigid body on it. And the watermelon has a trigger on it. So and they both have colliders. So if you check the collider for our agent, we have is trigger set to false, but for the watermelon, which is a prefab, we have set that trigger to true. And what we can do with that is we can say that the watermelon, which I've given the game tag melon, when our agent collides with any thing that has the tag melon, it's going to trigger on trigger enter, it's going to trigger this set of instructions. So when that happens, we're going to set the reward to 1. I'm going to print in the console target acquired so I know I can kind of see what's going on. And I shared this in a different video, but I love to play a little sound when my agent is learning. I think it's really fun to hear the learning actually happening. That way, if I'm working on something else, I can kind of keep an eye on how well my model's training. I highly recommend you do this. It's very fun. So after that happens, we need to destroy the tool prefab and also destroy the target prefab, the watermelon, so we can start that over once we call end episode. And again, as always, I've just put in some very simple heuristics so I can control the environment as we did earlier. All right, so since we're looking at the code, let's go ahead and take a look at our hyperparameters for PPO and for SAC. So these are pretty much standard. I tried a bunch of different things. I tried a regular environment. I tried using extrinsic reward. I tried using curiosity reward. I tried with memory, different combinations of those. And I did the same thing for the soft actor critic built-in algorithm for the ML Agents package. All right, so normally at this point in the video, I would show you guys how to load up the inference file from the automatically saved model that you just trained and use that to run the inference or testing phase of your experiment. But in doing this particular experience, I came across this very ridiculous error that I have not yet been able to solve. It has something to do with the gem file in layer 56. It's a whole big mess. And if I figure out that error, I will definitely post a video in case anyone else is struggling with that. But in the meantime, I wanted to go ahead and get this video up for you guys so you can see this cool environment that I made. All right, so I have some previous video of training I did, and let's just go ahead and look at the results that I got so far. So again, this is my tensor board, and so we can see that some of them performed extremely poorly. And some of them perform more well. And so while I was setting up the reward curriculum, I noticed that adding a small negative reward for existing actually made the model worse than it did better. So I removed that, and now we only have one positive +1 reward for reaching the watermelon target and a negative reward for accidentally falling outside the pin. So what I'm going to do is I'm going to deselect all the runs that had the different reward curriculum. And so now we can see here the different types of algorithms and how well they did. So the best one is this green line. I trained it for quite a while. And that is just a regular PPO with extrinsic reward. Just something very simple, no memory, no curiosity reward. Just very simple algorithm actually did the best. And so let's go ahead and take a look at what that training looks like. Okay, so what I found really interesting in training this environment is that it looks like the agent has actually figured out how to move backwards and prefers to do so probably more than half of the time. I watched this training go like for many hours over the course of the past few days because I was really interested and how this experiment would play out, since this is such a famous neuroscience experiment they do on monkeys and birds and other animals. Because the tool use demonstration doesn't only say, hey, this thing has learned how to get to some target, it involves some planning component that we think activates the neocortex, specifically the prefrontal cortex. So it's really interesting to see any sort of tool use at all happening in a reinforcement learning environment. And I think that something that would really help this, there's a couple things I think that would really help this environment and help the agent figure out how to do this a little bit better. First of all, I think the agent needs to be able to control the camera in all directions. So most animals use their vision and look around using a lot of different muscles in their necks, obviously, and stuff like that to gather information about the scene before they decide to execute a behavior. So I think that's one important change that may need to happen in this environment. And I also think that running something like a deep Q visual network might actually be better suited because the information that we're taking in is highly visual, number one, which a deep Q network is way more apt to solve. And two, we want to have a little bit more of a temporal component so we can allow this agent to start doing some of that planning technique. So hopefully in the future, I'm really looking forward to testing out some of those ideas as I explore more in this environment. And again, I'm sorry I couldn't get the inference inference file working, but if I figure that out, I will definitely post an update on that. Anyways, in the meantime, let's just recap again what we've done today. So we had an agent that was a sheep. It had to get to this target watermelon. It had to use a block or a tool to jump on it to reach the melon. It couldn't get to the melon without jumping on the block. We got +1 for reaching the target, -1 for jumping out of the pin. The model that did the best out of the built-in ML agents algorithms was proximal policy optimization with extrinsic reward. We used the vision input for one color camera, a 10 by 10 frame, agent velocity, and agent local position. The behavior the agent could take was continuous movement, looking left or right, and going forwards and backwards in that looking direction, as well as a jumping mechanism. So in training and testing, we randomly dropped in the agent, we randomly dropped in the watermelon, and we dropped in the tool in the same place to make it a little bit easier for our agent. So that was the experiment, guys. I hope you found this as interesting as I did. I'm looking forward to really exploring this more, and stay tuned next week for some more interesting demos. Don't forget to like and subscribe. Thanks for watching.